Ladies and gentlemen, for this afternoon, we start with Jens Groth, who's going to give at ZKProof 6 the keynote talking about memory checking in IVC-based ZK VMs. I had to look at it. Jens is also part of the ZKProof steering committee and has been helping us on almost all of the events before, after, during, very active in ZKProof and always helpful. Thank you so much for that, and go on with your talk. Thank you.
Okay, thank you. Okay, so so I recently joined Nexus. We're working on ZK VMs, and one of the performance bottlenecks we have is sort of like how do you check memory in the ZK VM? It's a folding-based ZK VM, so the problem is that whenever you do a sort of like one slice of computation, you try to fold that, then you don't know sort of like the global view of the memory, right? And then it becomes very expensive to check that. So I wanted to talk about ZK VMs and how to check memory in ZK VMs, and some of the ideas that have been floated in the space about how to do that and how to do it efficiently. So let's get started. So the starting point is a VM without the ZK, right? So you have some very well-defined way of handling instructions. So there would be some program, you give it out as input, you may have some input to the program, you may have some auxiliary input to the program as well, right? And then at the end, the instruction set architecture should say what is the output of this computation. And the auxiliary input, so if you come from the traditional cryptography community, then you would think, oh, that's probably a witness, right? And we wanted to do some zero knowledge and hide that. But recent applications actually also focus a lot about scalability and don't care about ZK at all. So the whole point is just that you don't actually need to explicitly give it to the verifier so they check it, right? And then you can also use that to get good performance because you don't actually have to check that as a verifier. So that gives you scalability. It does not necessarily mean you actually need zero knowledge, and some of these ZK VMs are actually not zero knowledge, so it's sort of like a bit of a misnomer to call it a ZK VM, but that is what we are doing in this community. I don't know what the implications is for ZKProof or the standardization, what we accept for that. Okay, so then ZK VM, right, would compute the output, but it would also give you a proof, right? So now you know that it's actually the correct output. It really has been produced by this computation. And there should be a matching verification algorithm that would look at the program and the explicit input X, but not get this auxiliary input, right? And then it will look at the output and the proof and say whether it accepts or not. And we hope, of course, that this would be a very efficient verifier, right? It would be a succinct proof that it would be very fast to verify, so you don't have to pay as much as recomputing everything from scratch. And if you look inside the way people design ZK VMs, then typically you would run the virtual machine on the inputs, do a lot of steps, right? Get the output, and then you would give that execution trace to a prover that then computes a proof. And we've really, these days, improving the proof efficiency a lot, right? So there's Moore's law that says the number of transistors per chip increases about 50% per year. And we haven't actually quite finished 2024 yet, right? But I'm predicting that we will have like more than 1,000% improvements per year these days. And I think you can sort of like see that what is considered good language in writing papers has been changing over time. So like back in the 80s, you know, you were thinking about like infinite time provers, right? They were unbounded in the computational time they could spend. I think these days we are sort of like, as the efficiency improves, right, we also have to be more and more precise about how we describe that efficiency, right? So we sort of gone from exponentiations per gate in an arithmetic circuit to, some quasi-constant field operations per constraint to now we think about like CPU cycles and what you're paying for that, right? I think we'll soon transition to saying that we actually want to do even more apples to apples, so we'll see how many CPU cycles does it cost to prove a CPU cycle. And what is the end game? I would expect that it's probably something like related to physics, like something, what is the, because at some point we'll think about hardware and things like that, right? And I think the ultimate performance indicator then is probably something like the energy per proved cycle. Today, it's still the case, right, that prover efficiency is the bottleneck. But again, it's really been changing what is a big thing to prove. So when I started my PhD in the 2000s, right, then I was working on voting, and the big thing was like a voter wants to prove that they have encrypted a valid vote and not an invalid vote, and that's what they're submitting, right? And it took a couple of minutes in a browser of that day, right? And so that was painful experience, right? Nowadays, those kind of things would be like, we just throw even the worst of the snarks at it, right? And it would be done immediately. So right now, I think, so like computations on the blockchain is what is expensive and what we're battling with. Of course, there's a lot of non-blockchain applications as well. And I'm hoping that in future, it's really everything that we will be doing with verified computing. And if you want to prove everything, then that's a pretty big computation, right? So there's a question, what do you do if you have like a long computation and you want to prove that? And an idea is basically that you would slice the computation up into smaller pieces. And then you would try to prove each of those pieces by itself, right? And then you would somehow glue those proofs together. And Paul Valiant in 2008 introduced the notion of incremental but verifiable computation, where he was really thinking about like, this is an extreme, right? So he gave this example, what if you have a computation that runs over 100 years? What do you do then, right? And probably you would want to, compute a bit, but then you would want to get a proof that you're sort of like on the right track, that nothing has gone wrong, there was no sort of like bug or something like that. And then you would prove another chunk with new equipment and so forth, maybe. So his idea was that you would have some starting input Z0, right? And then you would sort of like in chunks compute steps of this computation, and at some point in the future, you would have this Zn as the current output of the computation. And then you would want to have a proof that matches that, that all the computation up to that point is correct. And the prover for that would so like take as input all of the data in these steps, right? So it would take as input, so they would always take as input, so like what is the initial state, right? Because you have to link it back to the beginning, the origin of the computation. And then it would maybe take sort of like, which step am I working on right now? And then what is the output I have produced in this step, right? That's what I want to prove. And as a witness, you would then take the output from the previous step, right, that you're working on, so the input state, and whatever non-deterministic input you might have in addition to that, and then the proof that the previous step was correct, right? And then you would output a proof that now, okay, now I will compute this step, and I'll compute a corresponding proof that I've computed that step correctly. Okay, so I'm going to talk about using incremental verifiable computation for building ZK VMs. So here the idea is that this step function would really be a description of what does a virtual machine do, right? So it would be some number of steps of that virtual machine executing. So the starting point would be the program and the inputs to this computation. and then you would take some steps, right? And you would get Z1. You would take some more steps, get Z2, and so forth. And at the very end, you would get the output of this computation. Corresponding to that, you would then have the prover for each of these steps, right? That proves that this step has been computed correctly. And you would give that proof to the next round, and you prove, oh, if the previous round was OK, then I've computed the next step correctly, and so forth, until you have a proof for the final output. So I'm going to use this notation where, like, put this big box. So think of this big box as the ZK VM, right? That's the machine that's operating. Takes some inputs, produces an output, and produces a corresponding proof that the output is correctly computed. And we're going to do incremental verifiable computation, but sometimes there will be some other pre-processing that you have to do to determine what are the inputs you want to give to this computation. And in particular, there's a question like, do you really want to start with the whole program and inputs and so forth? Or do you want to do something else? So people often massage and, for instance, give like a hash as the starting input, right? And then it's basically just a hash of the program, a hash of the input, because that's much more compact to start with. And then you would over the auxiliary inputs you give to the incremental verifiable computation, you would then piece out that here's part of the program, here's part of the input, and this is what I want you to work on. And then, and maybe you would actually upfront also include the output Y in the digest, right? And then you actually, in the end, you're just checking, it's the final state that now the machine halts and accepts and says everything is great. And you may also do some processing, so maybe you have this IVC computation, it produces a proof, but maybe you then wrap it in a different snark because now Groth 16 is going to be standardized, and that's the thing that everybody expects you to produce. Right. So the problem I wanted to talk about then is the cost of maintaining memory, right? So the first idea that springs to mind is, well, okay, we have this virtual machine. It gets here's the 4 gigabytes of RAM that you need to work on, and here's the register initial values and the program counter and whatever other stuff, and then go and compute, right? But that's a really expensive state transition function, right? If it has to take the full memory at every step and then compute some CPU cycles and then, output again the full contents of the memory, right? And it has to have checks that all of that is consistent. So we would like to do something that's cheaper than that. And the natural idea is then, can we externalize the memory? So here, the idea is that instead of explicitly giving the memory as input, as a state that it works on, right, and it outputs the full memory again, instead we just take the CPU steps. And that's what we want to prove. And then whenever the CPU needs to access the memory, what we would do is basically say that's some auxiliary input. So we will say, hey, yeah, you were reading this address, and the value was 3 or whatever it was. And of course, this is much more efficient, right? Because now we only need to constrain the CPU, but we don't need to have the constraints on the memory. So that's certainly cheaper to prove. Okay, so let's try a straw man, which is of course very flawed, right? But so here's the idea. We have now a step function that describes this is how the CPU operates. Okay, it will have a state, which is maybe the register values and program counter and things like that. Okay, and then it keeps computing some steps of the computation, and whenever it needs to access memory, then it will ask out and get that as an auxiliary input. Okay, and we can of course run, this is perfectly fine as IVC computation, right? So we can have a proof that for every one of these steps proves that the CPU has been executing correctly. The problem is, of course, that a cheating ZK VM could just feed inconsistent memory accesses to the CPU, right? So maybe in the first step it says, the CPU says, oh, I want to write something, and the ZK VM then says there's no auxiliary inputs. Sure, now you have sort of like had the opportunity to write to this address and with this value, right? And then in the next step, it says, the CPU says, hey, I would like to read that address. And then the ZK VM prover just feeds it the input that says, now you are reading value star, right? And if they don't match up, then you have like an inconsistent memory that just doesn't correspond to a random access memory that's working well, right? And you would just get the wrong output. But of course, the prover is just checking the CPU steps. Everything looks great, and it would produce a valid proof. So we somehow need to protect the memory on behalf of the CPU. So what we can do is we can look at a more sophisticated step function. One that uses sort of like the CPU step function as a subroutine, but adds on top of that some memory protection mechanisms. So the idea, sort of like the very high level idea, is that whenever you are executing, there will be some sort of digest of the memory. And when you execute, you will update that digest to some new digest of a new memory. And whenever you get some auxiliary input that says, here is some memory write or some memory read, then you would, corresponding to that, also maybe provide some check information that helps to decide whether this is actually a valid read or a valid write. So this meta step function, the execution function, would then, for every memory access, it would check, is this a correct memory access? And if it's a correct memory access, then I will then call the CPU on that memory access and get the next step. Okay, so if we plug that in, there's a little bit more stuff to deal with, right? And the question is, of course, how do you implement these digests and these checks, right? So you can actually check the memory. But the high-level idea works out. Like, if this is actually something that protects memory, then we know the memory is good. And since we're calling this CPU function as a subroutine, we're checking that with a prover, right? Then we know that the CPU execution is good. So combined, that means the whole computation is good. And the first idea that springs to most people's minds is, well, how about we use Merkle trees, right? That's sort of like how we check things. So you would start with a memory. You would sort of like create a Merkle tree, a Merkle commitment to the initial memory. That's sort of like what you would feed in as the first digest. And then as the computation goes along and memory changes, then you would always update this root to the Merkle tree, right? And now you have like this digest that commits to the full memory of the machine. And then whenever you have an access to a memory cell, you basically provide a Merkle path to that cell to make sure that it is actually correct, right? And this is something this execution step function can check this Merkle path and say, yeah, sure, that is great. Okay, so that gives you now a step function that actually faithfully does implement a consistent memory and CPU. The problem is that it's expensive, right? Because you actually need to, now the prover has to sort of like look into this execution step function, right? And say, oh, there's some Merkle path, right? And I have to check that Merkle path, and it really blows up because, not only do you have to check that, but you actually have to prove that it's a correct path, right? So there's a lot of constraints to prove. So that's the bad thing about it. So I want to talk about a couple of other techniques that we may use to check memory. And for that, I need to be a little technical here. So I want to talk about a technique that's often used in this field to think about whether memory is consistent. And the idea is that you want to keep track of every read from the memory and every write to the memory. So think of these two sets here as and multisets, because you might have several accesses to the same memory. So basically, you want to have like a write set that keeps track of, these are all the writes I've made to the memory. You'll have a read set that keeps track of these all the reads. And you don't want to ever read from something that's not written before, so it's always the write set that is ahead of the read set. And when you read or write a value, what you do is you you find the last value for this specific address that you're interested in the write set, right? And shouldn't be in the read set, so you be where the write set is ahead, okay? And then you would take that value, and now you would add it to the read set. So it's now I've read from this cell, right? So it's now I've balanced out the read and write sets. And then you would take the new value that you're writing, and you'd add that to the write set. Okay, so the read is I want to balance out, so I will always read a cell at most once, right? So, and then even if I'm doing not a write and changing the value, I would actually still do a read, and then I would do a write just with the same value. So that's a way to simulate that you're doing reads and writes. So the point of this is that we have these two sets, the write set, which is ahead of the read set, and the read set, which is trailing behind and trying to catch up whenever you read something and you're not yet written something new to that cell. And the memory is consistent if those two sets are always aligned with each other. The write set is always a bit ahead. And then when the program is done, actually, we want to then do a final sweep over the memory and read out everything without adding a write. And then we would want those two to exactly balance with each other. Okay, and you can prove that if you do that, and if they balance with each other, then you've actually had consistent memory accesses. This is a tool to help us reason about memory consistency, right? So you don't actually want to explicitly, in any of these step functions, keep track of these read and write sets, because they're going to be very big. Okay, you want to have some digests of them instead. And one way to build this kind of digest was something called multiset hashing. So a multiset hashing function is basically a map from a multiset S to some group G. And you want a property that if you're taking two multisets and you hash both of those, then you should just be able to add them together, and you have the hash of the union, the multiset union of these two sets. And you also want it to be collision resistant, so it would be possible to find two distinct sets that map to the same thing. And I'll give you a simple example of such a set hash, okay, which is basically you take a hash function, map it as a random oracle that maps into the group, and you just, for every element in the set, you take this random oracle value, and then you add them together with the group operation. Okay, and you can argue that if discrete logarithm problem is hard and this is a random oracle, then you can't actually find any collisions, right? But it's very easy to see. It doesn't matter which order we're adding elements in. So if you get a multiset represented with one order of elements, or you get a different representation where they come in completely different order, you'd still get the same hash. I mean, still the same addition, right? Okay. So the idea now is that we can use these multiset hashes as the digests of the memory, right? So what we want to do is basically keep track of a digest that says, these are all the read set values. Okay, and we'll have a digest that says, these are all the write set values up to now. And we'll keep updating those values in the set when we do the step function. So what we'll do is, in every step, we'll keep track of what is the changes to the read set. What are the changes to the write set? And then we'll update the read set digest correspondingly and the write set digest correspondingly. And we'll sort of like keep doing that in every step function. And so like when we get to the end, we'll do this final read of the full memory. So we'll get these two sets to balance. And we can actually check whether they balance or not, because if they balance, you have those two digests match exactly, right? That's a property of the multiset hash function. And if the two sets are different, then you would have different digests here, and this check would not work. So it's a very nice function, right? And it's cheaper than using Merkle hashing, right? Because now, for every access to the memory, you're just doing one of these multiset operation, then that was just applying a hash and then doing an addition in the group, right? So you actually end up doing 2 hashes per memory access instead of doing a logarithmic number of accesses per memory access. Okay. You may complain that that's still expensive. Should it really be that expensive, right? And somehow, it ought not to be. So if you think about a monolithic stack that doesn't slice anything, what do you do? Well, you use some offline memory checking techniques, and it should cost like a constant number of field operations that you need to check per memory access, right? So what is all this stuff here? Can't you really do better, right? And the answer is that you can do better, and it's sort of like interesting. It is a technique that's been discovered, I think, several times independently. So remember, we have these read sets and the write sets that sort of like track the memory changes to the memory. And we want to make sure that at the end, we have a balance that the read set, the multi-set, the read set is exactly the same as the write set. So all we need is an efficient check that that's the case, right? And when we do memory checking, right, then we can use cool things like the lookup arguments, which, by the way, I often see that attributed to Ulrich Habeck, but there was also a paper by Liam and Jonas, I think at least are 2 of the authors. Yeah, there we go, which did that slightly before on ePrint. So for all of you that are referencing them, please update your references. So the problem we're facing, right, is really that we want to have some way of figuring out are these 2 sets, but of course they will appear in very different order in the execution, right? I mean, we'll write sometimes somewhere and then we'll read at other times, and those might be out of order with each other. So the question is, okay, how can we check that? And the lookup argument suggests the following check that will sort of like map all these tuples of memory accesses to some field elements in some whatever way. And then when we want to check if these 2 sets of elements in appearing different order are the same, what we can do is basically we can compute this formal sum here in indeterminate capital H. And as I'm sure you're familiar with, right, the standard way to check these kind of identities is that we pick a Fiat-Shamir challenge and plug it in and see whether these things add up. So let's try to do that. Well, there's a bit of a problem when we've sliced the computation, right? So think about like, okay, I'm doing incremental verifiable computation. I want to prove this kind of thing, right? If it's an early step, right? And I know H, then I can cheat in the future, right? Because now it's not a challenge anymore. It's sort of like a known challenge, not an unknown challenge. Okay? Instead, if we say, let's generate that challenge very late, right? The problem is that then in the earlier steps, I don't know it, so I can't actually compute on it. And there's an additional problem, which is that like it's an incremental kind of function. There's nobody who has a global view of everything at the same time. Right? So it's like you can just sum whatever you can. Sum is just like your slice of the computation. Okay, so let's try to solve this problem. And for that, let's just remember, right? We have this kind of like, I've split the step function into two parts. One which does memory checking and so forth, right? And then another one that does sort of like the CPU checking. And it's interesting to note here and important to note that the execution trace itself is independent of the challenge. Right? You just run the VM, and the VM doesn't know anything about the challenge, right? That's all like proof stuff. So you just run the execution, right? And it would know exactly which kind of memory accesses and at which time and which value and which address and so forth we touched. Okay, so all of that can be determined in advance. So the idea now is to incrementally build this challenge. And this is an idea that's appeared in several places. I think the first one, I found a reference on a blog post by Lev Sukhanov in it was a forum post, I think. And then I know it's in the Mangrove paper, which is kind of recent. And I mean, and the history why I'm talking about this, because I came up with it as well. So that's sort of like, it's been rediscovered many times. So the core idea is to sort of like do a two-pass through the memory for this checking. And first, we'll do some pre-processing by the ZK VM prover. So it'll run the VM. It'll learn everything that the CPU sees, including all the memory accesses. Now it'll commit to all of these memory accesses and whatever the CPU sees. And at that point, once we've committed to the execution trace, we'll build a hash chain using all of those commitments as input, right? And out, we will pop, in the end, the challenge H that we're going to use. And only now do we start the incremental verifiable computation. So the idea is that now we want to actually use this challenge H, right? Because now it's been chosen after everything is committed, so that's great. But at the same time, we want to verify that it's correct. So this step function now, it sort of like does all these kind of execution checks, and it also recomputes the challenge, right? And this is why we used commitments and why we use hashes, because that's actually a very small computation, right? It's like maybe the commitment is a Peterson commitment, it's some group element, you have a field element that you're hashing together and so forth, right? So that's fairly cheap. So we can do that in every step without much extra cost. Okay, so now we're almost there, right? We want to do this kind of test. We'll just plug in this pseudo-random challenge H. It's great because we committed to everything in advance and then computed the hash chain, so now you can't cheat and change the memory or something like that. Okay, the IVC recomputes the whole hash chain and checks that you are getting the right challenge, so you couldn't cheat with the challenge either, right? And then finally, the ZK VM prover, we want that to keep track of the log-up sums, because every slice sees some of the memory access, but not all of them. But the point is, it's just a sum, so we can just keep a running sum where we add the contribution for every slice. So it looks like something like this, right? So we're doing all the recomputation of the challenge H, and then we have running sums that says, like, this is the log-up sum of all the reads. This is the log-up sum of all the writes. So we'll, at the end, get the sum of all the reads, the sum of all the writes, and then we'll check that those two match up. And if they match up, we know that read set is identical to the write set. Okay, and it's all sort of like a reasonable efficiency to compute, right? Because the hash chain is cheap to recompute. There's some cost in the pre-processing because you have to compute all these commitments. I cheated a little, so the title in the program says folding-based ZK VMs, and I changed to IVC. And the reason is actually because I came from a folding context, and there you automatically have those commitments anyway, so they come for free. Okay, so this is like fairly cheap, and the only remaining cost now is, well, you have to compute these contributions to the lookup sums, right? But that's just a few field operations per memory access. So now we're down to a constant number of field operations per memory access, just like we have in monolithic snarks. Okay, so as you can see, like the efficiency, we went for better and better efficiency, and we're ending up with, if we do this kind of like two-pass memory checking technique, then we are recovering what traditional monolithic snarks can do, namely getting a cost of a constant number of field operations per memory access. Okay, there's a bit of a cheat going on here. So there's a little bit of a cost, which is we are actually moving a little away from incremental verifiable computation, right? So if you do like Merkle trees and so forth, sure, you don't need to think about it in advance. You can just start processing, compute those Merkle roots and things like that, and Merkle path along the way, and keep on going. If you're doing the multiset hashing, you do need to flush out the memory with having like a final, make sure that you read everything so the two sets balance each other at the end. So you can start going, but at the end you have to do some extra work to finish up the proof. And if you do the two-pass offline memory checking technique, right, you actually have to run the first pass first, and then you do everything once you know the challenge, right? Which means that now you don't have incremental verifiable computation that can go on for 100 years, right? Because you said, this is where I stop. And you would have to come up with some other ways to do it if you want to continue. So anyway, but I think at the end of the day, I think we should be happy that we can split up the computation and still have very good efficiency when we check the memory. Okay, thank you everybody.
I think we have time for questions. If anyone has any memory checking they want to do to come up with questions.
Check, yes. Are there other interesting constructions of hashes for multisets besides the nice random oracle-based one?
The ones I know of all fall in this kind of like category. There's a lot of so it's a fairly old technique, so like when it was first introduced, and back then people were not using elliptic curves as the group, but they were using other types of sums. So people have been thinking about that, more from a knapsack kind of problem. So you would do maybe these kind of additions modulo some modulus n or something like that, and then hope to have some other assumptions about these sums, so you couldn't actually compute two sums that balance out.
Okay, thanks.
Hi, this may have been just something simple I missed, but what is preventing a malicious prover from swapping the order of adjacent memory operations, like say a read-read-write versus a read-write-read? Because I would make the sets the same. That makes sense?
I think it makes, yes, okay. I think I get it, okay. And I think the way you prevent that is, so you do actually, so you have to do some extra checks when you're doing these operations here. And one of the checks that you're checking is that whenever you have two accesses, you're pulling something from the write set and put it in the read set, you would check that the timestamp of that thing you're pulling out is an old and previous value that does not surpass the current timestamp.
Okay, so like we're enforcing some strict ordering on the memory partition. Okay.
Exactly.
Thanks for the talk. I was wondering, why do you need the logarithmic derivative transformation as opposed to a product-based permutation check?
So if I understand your question correctly, it's sort of like, are there other ways we could check memory instead of doing the lookup arguments? Yeah. And indeed, there's one technique that's also been used a lot. It's sort of like invariance of roots when you compute a polynomial by multiplying all the roots out, right? And you could use that check and it would work just as well. I think there's something a little easier when you do the step function in adding things up rather than multiplying things together, but that's the only reason, otherwise it would work at essentially the same performance.
Thanks for the talk. When you use the roots for this permutation check, in that case, is there still the problem of producing the challenge, or?
Yes, that would be exactly the same.
Okay.
Yeah. So the same kind of constraints that whether you know it early or late or whatever would apply. Yeah.
I see. Thanks.
You still have to do multiplication, no? Because you have to do inversion?
That is, yeah, that's true, yeah.
Else?
Okay.
Afternoon session. Good.
Gotta work off the lunch. Okay, I promise this isn't a trick, but one kind of small thing I've been stuck on trying to think about this sort of thing is how to validate the timestamps being updated correctly. So you need like the timestamp for a given read or something to be greater than the timestamp for the previous read to that address. The thing with this is that ordering is a tricky thing to do in a finite field context. So do we have to stick a bunch of range checks in there? Is there something else we can do there?
So there's quite a lot of people that have been looking into range checks. So what are the different techniques you can do that? So one technique is you do lookup, so you basically decompose whatever the delta is into small enough chunks that you can look them up and make sure that they are greater or equal to 0. The other one you can do sort of like a double sorting kind of trick. So you sort all, so say you have many range checks you want to do. So you sort of like, you just write them out, you sort them, you would get now much smaller deltas. Now you sort again and you get even smaller deltas, right? And so like repeating that enough times, it all gets down to zeros and ones that you can prove in a different way. So that's another technique. A third technique is that there's been sort of like various works on sort of like trying to do batches of ranges and taking the sums, and you don't get an exact range check, but you get like an approximate range check with that, and sort of like relies on expander graphs and things like that. So there's a lot of different ways to do range checks, yeah, it's so like so when you're trying to squeeze out the last % of performance, right? Then that's the kind of thing you dig into.
Thanks.
So yeah, about that, if you have a counter, you're keeping track of what operation it is. You start from 0. You constrain that you always increment it by 1. So maybe you could, like, if the modulus is large, you could just, under the assumption that you're not doing like 2 to the 256 steps,
so you can sort of like bound the ranges that could possibly be, right? But if you have like an old timestamp and current timestamp, it could sort of like be anywhere in the range of like 0 to step 1 million or how many steps you've executed, right? So I guess what you're saying is you can sort of like make sure that it's not a huge interval, but a smaller interval that you have to look up.
I'm saying, can we just enforce that we start from 0 and are incrementing the timestamps by 1? Maybe that suffices if the modulus is large.
It's not a timestamp, it's an access count, right?
Yeah.
It's an access count, so you always increase by 1. That's what you were saying.
Timestamp access, yeah, some counter you're always increasing by 1 with each operation.
Yeah. Okay, so the
access count
thing,
is better.
yeah. Okay, so you can do things like, you know, can I do, for instance, and for every memory address can have like an individual counter that just says how many times has been accessed. That would be one way.
Or it can be one counter of the total. So far, there's been total memory access.
Right. Yeah.
And just check that.
Yeah. So and the answer is yes. You can do all of that. You have to be careful though.
Yeah.
So.
Thank you, Jens. So the title of the talk was memory checking techniques for IVC-based ZKVMs. But it seems like we lost the IVC property, pretty much, right? And so do you have a sense about how expensive it might be to recover it?
You're asking a really hard question. Who are you?
Why do you use the IVC property? Because you're taking 2 passes?
Yeah. For example, the square at the bottom right? We dictate a bound on the computation.
Yeah.
So.
I mean, you can do things that, but essentially I think what it boils, so I think you can do things where you basically, maybe you would have like, sort of, say you want to have like these 2 passes, right? So you could sort of like do a pass, and then you could have an overlapping pass that starts a little later and ends a bit later, and you can sort of like, and maybe you can do things like where you amortize and move the memory over to something else that sort of like corresponds to the new pass. So that would be one idea for doing that. I mean, so that's sort of like one way you can try to massage this technique to still work. It's sort of like a bit of a hack, but I think it's probably the best I can come up with. The other question you can ask, I mean, so often you will find computation is actually there will be more execution steps than there's a memory consumed, right? So if you have something that just uses little memory anyway, right, then you don't care about the memory, right? It's the sort of like the execution cost that really matters, right? And then you just pay the price for the memory.
Right. Okay, thank you.
More questions? Okay, thank you so much.
Okay, thank you, everybody.